Apparently, the wave form moves through the water, and the water itself stays pretty much in place. Let's do another experiment and find out how much the water in a wave does move. We'll use a wave tank again, but instead of using wind to make waves, we'll use a mechanical wave generator. The energy that makes these waves is provided by the regular movement of the wave generator. These simple waves are easier to study than the complex waves we find in the ocean. A small ball floating near the surface of the water behaves in much the same way as the larger ball did in the ocean. Let's watch it in slow motion. Each time the high point of the wave, called the crest, approaches the ball rises and moves forward with the wave. As the crest passes and the low point of the wave, called the trough, approaches, the ball moves down and backward. After each cycle, the ball is back to just about where it started. The motion of the ball is almost circular. This means that the water on which the ball is floating is moving in a similar circular orbit. At the water's surface, then, the effect of a wave is to make particles of water move in circular orbits. Now we can see what happens below the surface by putting weighted balls into the water. While the uppermost ball moves in an almost circular orbit, the deeper we go, the smaller the orbits become. The water moves less and less. Finally, at a certain depth, there is no measurable motion at all. If we measure the depth at which a wave no longer moves the water particles, we find that this depth is equal to about 1/2 the distance between two successive wave crests. This distance is called the wavelength. The deepest ball, which we don't see move, is at a depth greater than 1/2 a wavelength. The upper balls are less than 1/2 a wavelength deep. Now we know something about how water moves in a wave.